We're going to switch gears a little bit and start to think about the application of the digital twin that we are contemplating here. And our next speaker is Karl Mitchell. So Karl got his bachelor's in physics from Leicester University. He got his MS and something called a DIC, which I learned was a diploma of the Imperial College London. Does anybody else here have a DIC? No? No. Do you have a DIC? Okay. What's the chance? And his PhD from Lancaster University. He's a physicist, a remote sensing specialist, specializes in fluid mechanics, thermodynamics, and remote sensing. He's been at JPL for quasi 25 years. 19 years, okay. He has many roles. He's a scientist. He works a lot in proposal development on behalf of himself and the whole science group in Planetary Science up there. He's involved in multiple NASA missions, a lot of experience in mission formulation. He has been a project scientist on a discovery proposal to Triton in the past, and he's working on a current New Frontiers concept. All yours.
Thank you.
Oh, and he's going to tell us about the overview of planetary mission formulation.
Thank you, Mark. And I really do want to thank, in particular, the staff of the JPL Innovation Foundry, because I've been working with them for a large number of years, and my pathway into initially science formulation and then broader aspects of formulation is largely thanks to them, especially Al Nash, who provided some of the material for the talk today, but also Troy Hudson, who's impacted my thinking in a wide number of ways. And so there's an emphasis here on planetary, and I'll get back to why that's important, but I will say that there are differences in culture within the science mission directorates between planetary science, earth science, astrophysics, and planetary is kind of an extreme member, as we tend to be driven more towards the deductive hypothesis testing approach to science rather than consensuses about what should be measured. And so aspects of what I'm talking today will be about the challenges that scientists have within that framework, and then how the scientists work with the data scientists, so the natural scientists work with the data scientists, and how the data scientists work with the engineers, in order to come up with a competitive mission. And I say competitive, it doesn't have to be in the competitive mission framework. It applies to flagships like Europa Clipper and the like as well. It's just, the reality is there's always some level of competition. Okay, so what is formulation? This word was a surprise to me when I came to JPL because I didn't have any idea what formulation was. So it is the earliest stages of a NASA mission. There is a systems engineering handbook that basically says that pre-phase A concept studies, which is the first part of formulation, is the purpose is to produce a broad spectrum of ideas and alternatives for missions from which new programs or projects can be selected. It's also to determine the feasibility of the desired system. Feasibility, not necessarily proof. At these pre-phase A stages, there's often some fuzziness. Develop mission concepts, draft system level requirements, assess performance, cost, and schedule feasibility, identify potential technology needs, and scope. Bit dry. Reality is you're trying to pitch something that's going to sell. And there are a lot of different bounding conditions to that puzzle as to what sells. But in the end, it comes down to technical feasibility. Will this fly? Will it work? NASA desirability, and I say that NASA desirability, it's actually the science community to a large extent that pushes that NASA desirability and sells whether or not certain areas of science are more desirable than others, certain goals and objectives are more valuable, and the project viability. And in the end, it's about satisfying all these needs. And you can imagine when you ask a scientist what they want to do, what they pick is something that's way off the chart in one direction. And it's about bringing them back into that approvable space through a series of iterations. I say a series of iterations, it gets quite big, until it gets to the stage at which you've got some concept that's low risk, fits in the cost box, doesn't disobey the laws of physics. That's an important one. It does happen sometimes that people propose that. And at the end of the day, you want to win and not regret it, because unless the work that you've done is robust, if you win and then suddenly your mission ends up costing 9 times more than there was originally proposed, that creates problems for everyone. Not just you, but NASA as a whole. Actually, it may be good for you to a certain extent because your institution may have money thrown at it until you fix it. But in the long run, it's bad for everyone. So how do we conduct these trades? There are, again, bounding conditions here. Cost is absolutely critical, capability is critical, and then science is critical. You need to conduct a series of trades in order to iterate towards this solution that really does fit in the box. And I want to draw your attention to the internal components of this. Engineering is a really broad envelope here. You can imagine from a modeling perspective, if you consider all the subsystems, you've probably got at least tens of models for how different things work and interact with each other. What engineers don't appreciate, scientists often don't appreciate that. What often engineers don't appreciate is that science is much the same way. There are lots and lots of different objectives you can go for. There are different hypotheses you can test. There are different models of how systems work. And in the end, science is normally about resolving and distinguishing between those models. So, just a preview to what happens with digital twins. There are a lot of models we're talking about here that can interact with each other. And it flows up as well through management. I mean, if you spend a lot on your science and engineering and don't leave anything for management, when something goes wrong, when you've got a risk that is realized or even an unknown risk that comes along, you need people that are able to address that. You need to then control the cost. I'll also note that this is an area that I'm not going to go into too much. A lot of it's also about storytelling, and we often forget that. Science doesn't sell itself. Even engineering doesn't sell itself. You have to convince people that things are low risk. You have to convince people that things are valuable from a scientific perspective. So there's also this rule of communication. And in the end, you have to present a package that not only is technical feasible, but is also marketable. And so there are a lot of these competing concerns, models both engineering componentized as well as conceptual that can even be a storytelling model, Disney, Once Upon a Time level of storytelling, that all need to be coupled. And so there's a huge number of subsystems involved. With all of this, though, in the end, it's the science that drives us. Ultimately, it comes down to what is the gain for society? What is the gain for the community as a whole? And the key to remember, and you always have to rein back, is that you will run out of money well before you run out of science. So those trades are often extremely painful along the way, and you end up not being able to hit what you aspire to. So where do you start on this process? Well, we use a thing called a science traceability matrix. This is a table in the simplest way, and it's a requirement from NASA. The intent is to contain all of the high-level information to understand why a given proposal is relevant, what it purports to accomplish for science, and how it intends to accomplish it, and what expected products and knowledge will result from its success. That's asking a lot from a single table, but it is done to a certain extent. It's also a NASA requirement. I won't read this out, but they define certain columns, in effect, in a science traceability matrix, and their interrelationship between them. Beyond that, I always think of it as a common framework for scientists and engineers to work together on a shared problem. At the left-hand side, there's what we're aspiring to in the science, and as you go more and more over to the right, in this table, and I'll show you the template in a second, you get deeper and deeper into deriving requirements and eventually inform the engineers what they need, and then the engineers will attempt to meet those requirements or exceed those requirements with a performance. But it's a tool for storytelling as well. It's a tool for negotiating requirements, and ultimately, once it's submitted, once it's seen by HQ, it's a communication for mission definition and completeness. It does not necessarily state if the mission is capable of meeting those requirements, of which there are a whole load of other models at the end. What's the reality? Well, people see them as a requirement. They often don't want to work with them. They are often generated retroactively in order to justify requirements. And they're not always used during formulation process to actually inform trades. I find them useful. Not everyone likes working with them. As a result, they're often very limited in terms of both the science that they represent and the traceability from column to column, which is a bit of a problem. But I would advocate that if you end up being on a mission, you start developing this early, because if you can embed it into your culture quickly, it becomes a useful tool in order to facilitate that communication. This is the standard NASA template that existed in proposals for years. So you get the idea. At the left, there's science goals. The examples are not very useful. Goal 1. Science objectives. These must be achievable. Goals are more aspirational. Then the physical parameters. And that, you can imagine, a science objective, the leap to the physical parameters is quite complex. You know, justifying that you will get the answer to a question, that you will be able to test between different models. There's a big story there from that objective, you know, how do Enceladus's plumes work, distinguish between these different models, and those list of physical parameters. Physical parameters to observables, yes, that is a data analysis problem, but you can also perceive that there is a link between each of these columns that is reflected by another model. Again, the proliferation of these models is a common theme. Instrument requirements. So obviously you've got observables, you've got the data that you want to collect. Then it goes into a list of what it requires the instrument to do. And I'll skip over the projected performance because that's not always put in the same way. And then mission requirements. What do you need the spacecraft to do throughout all this time? I note that with the way that NASA evaluates missions in pre-phase A studies, there is an excess weight on Form A and a lot of and a little less weight on Form B. That flips around. So Form A is the evaluation of the science, and Form B is the evaluation of the science implementation. Huge amounts of work go into those left two columns there, early on in formulation. And it's often underestimated the hundreds of person hours per objective that go into developing those objectives before you even get to further along there. So I say goals and objectives. So to be clear, a goal is understood to have a broad scope. It's the big questions. It's the things that one mission probably won't actually answer on its own. Is there life on Mars? How was the solar system formed? It can be a smaller part of that, but in general, it's more open-ended, it's more aspirational. Whereas an objective is understood to be a much narrower focus part of the strategy to achieve this goal. Which model of the universe, and we're talking about whether we model the universe or not. We, of course, do not attempt to model the whole universe, but we try to break it up into manageable bite-sized pieces. And that's what these objectives tend to be about. Distinguish between these three competing models for how Enceladus's plumes work. Plume works, I should say, singular. Anyway, it says at the bottom here, and this often people miss, proposed investigations must achieve their proposed objectives, but an investigation might only make progress towards a goal without fully achieving it. So again, this objective, it's not only narrowly focused, but it is achievable and verifiable. And that verifiability is absolutely key to winning proposals, because otherwise you get proposal team haven't demonstrated that the objective will be met. So, what makes a credible mission science objective? And again, I tend to start from here. The goals side of things is often about linking to the decadal survey. Those goals are to some extent provided for us. We have to interpret them to some extent. But in terms of the scientific method, mission objectives typically encapsulate questions, testable hypotheses, and verifiable predictions. Objectives should have a clear path towards, ideally, I say ideally because that's not always the case, deductive science closure. Now, deduction is the art of testing between known hypotheses. Reality is you often don't know what the hypotheses are, or you present members. There is a whole philosophical debate here about what makes a really good objective, but you need to be able to demonstrate that you will achieve it, whatever you set your own homework as. And it has to be based on new data. What's the point of proposing a mission if you don't need new data? Leading to fundamental conclusions about cause and effect that advance scientific understanding. And to be implementable, hypotheses and predictions should ideally be defined. And this is where VVUQ comes in and starts to connect to the engineering world as a data-driven mathematical model. If parameter X is greater than such and such, this means that that hypothesis 1 is true. If parameter y is below such and such, there's obviously an issue with potential for degeneracy here, but when you're trying to demonstrate that something will work, you need to define some sort of thresholds in what you measure in order to test so that whether something or not is true. So this is an abstraction, as a very linear abstraction of the scientific method as an ongoing process, which is a fairly common graphic that's on the internet from various places. And in the end, the seeds of ideas come from existing theories and making observations, normally observations from past missions. Then you think of questions, formulate different testable hypotheses. Again, this is very much in a deductive framework. It may not be the only way to do it. Develop verifiable predictions. And then the mission in terms of the scientific method is a tiny little chunk. You're collecting some new data that allows you to get to the next stage in scientific information. You draw conclusions and then you define and refine your theories. The way I do it is I lay out the question, I list the series of competing hypotheses, I propose predictions, which again are normally inequalities in some sort of parameters. And then from there I can derive the physical parameters that allow me to distinguish between those different objectives. But again, it's very much a data uncertainty qualification problem when it comes down to presenting it in a mission framework. And again, I mentioned if the critical data already exists, there's no need for new data, so you have to iterate. And frankly, a lot of the ideas we come up with for missions, it turns out that once we dive deeply into them and try to devise a mission, it turns out they're somewhat moot. Someone's already answered that, we just haven't realized it. The data is there. That's what data analysis programs are for. Reality of the scientific process. You end up getting these massive loops of iteration, and it's only when you don't have to loop back early on in the process that it can lead to a potentially winning objective. For those that are into the engineering world, actually this sort of thinking, this sort of reasoning is very similar to design thinking. You define the problem, you research it, you brainstorm ideas, you plan a design, maybe a solution already exists, so you've been barking up the wrong tree, you focus on something else. You create a model or prototype, you test and evaluate it, and then assuming that it closes, assuming it does what you want, you deliver the product. Science and engineering logic is actually not that different. It's just that there's this deductive part at the start that is perhaps a very different paradigm. So, what makes a good objective? I was given permission to talk about this particular objective by the PI of Psyche. Psyche is a journey to a class of asteroid that we hadn't visited before. It's an extremely dense object with a high spectral signature for metals that have made people to suspect that it may actually be the core and the outside has been stripped away. Very fascinating place. So this is just a snippet of their science traceability matrix. And in effect, what they're trying to do with this first objective is to determine whether or not Psyche is a core, to verify that preferred hypothesis, or whether it's actually something more primordial, that it didn't come about due to removal of the outer envelope. And you'll see that there's a lot of explanatory text in here. You can imagine with a mission with, say, 4 or 5 objectives and loads of measurement requirements stemming from each of these objectives, that this table becomes quite big. And yes, it's a fold-out and it's got very small text. But again, it's the process by which you negotiate with engineers. So it features a fairly clear link between the goal and the objective, demonstrating a logical flow and traceability. By reading the objective and reading the goals, you can understand how they relate. You could write whole essays on how the goal and the objectives relate, but at least it summarizes the important elements. It clearly states 2 hypotheses. Was it a molten core, and did it instead accrete from primordial material? With, in effect, qualitative predictions that will inform what measurements are to be made. The science traceability matrix doesn't show everything. It doesn't lay out this hypothesis prediction state in an uncertainty framework or anything. It has these nice explanatory paragraphs, and as I say, it's qualitative. It's got no numbers at this stage. Some do, some don't. Some say if A is greater than 1, it means this hypothesis is true, something like that, but this one doesn't. Here's an example based on something that's a bit closer to my work. I published a paper recently proposing a new model for how Enceladus's plumes work, and there are 2 competing models out there, and I want to distinguish between those and demonstrate whether or not my model is more valid than these alternative models. One model suggests that the ice to vapor ratio coming out in the jets is going to be low, They could be fissure or point sources. These are Enceladus's jets. We've got points along them that look like they may be the source for them, but other people have said they're long fissures and they're completely open and there aren't points. It's more of an optical illusion. They'd be superthermal, so they'd be faster than you might expect given the heat, faster moving. And you don't require any kind of special additional plume in addition. There's another model that actually absolutely requires fissure sources, would have even lower amounts of a lower ice to vapor ratio. And again, a coplume isn't required, a subtle difference here, but all of these have different quantities in prediction space. And our model suggests that ice to vapor ratio in the jets, maybe not the plume as a whole, is very high, that it would be point sources long. Again, all of these inform observables, that they will be superthermal again, unlike the middle model, and a coplume will be required. So again, this is just a demonstration that there are predictions from which you derive things from. Each has consequences, quantitative consequences for the observables, jet content, etc. So this one objective has three models that are all competing with each other. I think that's the key here. Each hypothesis within a deductive framework, which is normally used for planetary missions, is represented by a model. When we go into the complexity of the things, the tectonic framework that this is all in also affects all those models. And so you could imagine from the science perspective, there are a lot of couplings going on between different models, different processes, as to what will be valid and what the observables will be. So, conceptually, hopefully I've laid out what is an objective. One might think of it in engineering speak, in NASA engineering speak, as a level 0 requirement. We go straight to the level 1 requirements when we're defining flow down of logic into the engineering world, which is the precision, accuracy, etc., with which you measure parameters, the domain over which you measure them, etc. But there's a whole world between the level 1 and the level 0. So again, this is a rotated version of the science traceability matrix with a mission traceability matrix. You go from the objectives, you define your measurement requirements for physical parameters based on this hypothesis prediction space. Then you relate those to observables, which is a data inversion model. When you're defining the flow down, it's actually an inverse problem. When you're doing the data's efficiency, it's a forward problem. You get instrument requirements and mission requirements, and it's actually how they couple that define how well the quality and quantity of the data you get. And then there's this whole mission traceability matrix that goes on further. I won't go into too much detail here. But the reality is every single one of these arrows represents a model. It can be conceptual, it can be scientific or engineering. Most of the time it's scientific or engineering. The up arrows are requirements, the down arrows are performances, but in the end, one's a forward model, one's a reverse model. And each of those models have different levels of maturity. We don't do stuff that's routine in NASA missions generally. We do things for the first time. Some of the time that requires new technology. Some of the time that requires testing hypotheses against each other that haven't actually had codified models before. Some of the time, new models come along while you're working, but there's a lot of models in there. And in principle, every model is coupled. And in order to iterate towards that ideal solution, they have to be solved iteratively. Ideally, this should be done within a rigorous VVUQ framework, but that's not always done. In fact, I haven't seen any situation in which it's done in a complete sense of the word. But you could imagine how it would lend itself to a simulation framework and maybe even a digital twin framework, depending on whether you meet the requirements for whether you're getting new data which tests your models along the way. Just an aside, this isn't just about natural science connecting to engineering. There's a whole data science interaction here. And for those of you that are familiar with it, there's this concept called the data information knowledge wisdom hierarchy. And those levels of data, of information, knowledge and wisdom actually relate quite closely to the columns of a science traceability matrix, which I personally find quite fun as a concept. And so, the goals are normally about the why, the objectives are normally about the scientific how, the information is normally about the what, and the observables are really about the data that you collect from your mission, at least within a mission framework. And for those of you that aren't in the planetary science community, I've also included the equivalent data product levels for different communities here. So hopefully you can anchor yourself in something that's more familiar to you if you're in earth science or astrophysics. And again, the examples for science goals are validated causal models. For science objectives, they're really tests of models. For physical parameters, they're normally maps of parameters. I say maps in the most general sense. And for observables, they're observations. And again, telemetry is all the way over there as well once you start really implementing the mission. For those that are used to the data, information, knowledge, wisdom hierarchy, you can put it this way as well. We can switch between them. And I will note that over on the right, nearly every term over there on the right is something that is defined within NASA AOs as requirements. And so when you see things like impact of state of knowledge, significance, there's a connectedness between all of this tissue that allows you to relate what you're putting in a science traceability matrix to the evaluation criteria that NASA asks for. And over on the left, we can also discuss the relationship with DIKW and what makes good practice for defining these different levels. One of the things I've encountered is that when you go to a group of scientists and ask them to do science, they drop in at the observables levels. So I would strongly advocate to begin at the beginning. Don't just say, I need this resolution to do this work. Prove it before you even get started. Starting in the middle normally results in a convergence problem. You can imagine if you start with, I need 100 meters resolution, you've got to validate that that will achieve your objectives. You may have overspecified it, you may have underspecified it. So you can imagine that flows to the left, and meanwhile the engineers go on and they design to the right their system in order to meet the requirements you state. And then eventually it loops back and they iterate and, oh, we've achieved your observable. And then the scientists say, oh, actually, we underspecified this, it doesn't meet our objectives, we're going to have some requirement creep here. Or we overspecified this, so we've ended up spending designing a mission that cost $10 billion. So always, if you can, start on the left. Not only is it unverifiable in the first instance, but the requirements tend to be unstable. So scientists start from first principles, flow over. Engineers, if you put too much pressure on scientists, they will start from the observable. You have to work with them, and it has to be a collaborative effort here. As I say, the result is normally excess cost or requirement creep. Often scientists will induce this observable, and I was going to step back, not to talk too much about science philosophy here, but induction tends to be experientially derived. And one of the challenges I see in formulation is that scientists come in with their experience and they immediately know what they want, but that's part of what causes this issue. So they should be encouraged to take time formulating their objectives before deriving them. But let's do it the proper way. So flow down starts with a specification of a physical parameter based on prediction verification thresholds stemming from science. So level 1 requirements. As I say, I like to go to level 0, but then they have to collaborate to iterate towards an optimal design. Even if you do it in the right way, there's going to be iterations. Do we meet these requirements? Do we have sufficient margin that the risk is low, etc., etc. The faster and more precisely the team can iterate, the more rapidly they converge. And the part of the problem is it's normally done in a piecemeal way at the moment. And partly because NASA mission science is often unique, but partly because when you start thinking about this problem, the framework, the number of models, it seems overwhelming. And in the end, it's easier to compartmentalize for most people. We don't have a common framework for addressing these issues, at least not for these very unique missions. If all those models that link the elements could be coupled in a common framework, we would be working in a much more efficient way. Now, is the effort to work in that common framework, does the overhead involved in that preclude that? I don't know, but maybe we can find out a bit in this workshop. So, what if there was this framework allowing the trades to be explored concurrently? We could benefit massively from that. To some extent, JPL's TeamX does this in their engineering. They produce models that they're very abstract in the way they interface with each other. They really just pass cost, mass, power, or at least energy profile, and data between the different subsystems, like the power system and different instruments and everything else. So, there are engineering frameworks for doing some of this. But I think what we're talking about within a digital twin paradigm is a little bit more ambitious than that. Because, again, TMECs work in this way. But what is missing is instrument functions in detail, observational models, not just how the spacecraft looks, but also how the data is returned. So the science inversion models, the observables to physical parameters and results, and then the hypothesis test frameworks. And the story is, when I was working Trident, we had this very challenging problem of demonstrating whether or not we would be able to detect an ocean under the surface of Triton in a single flyby. It was hugely challenging, and it turned out that from the existing models, there was a high risk that it wouldn't work from the existing models. And in the end, what we did was we had a really capable scientist / engineer working with other scientists and working with a VVUQ specialist, and came up with a model that took it from the instrument requirements and the mission design all the way to hypothesis-based testing. So there were less of these steps in the process at which unnecessary errors were being introduced due to the nature of breaking up the problem into too many compartments. And he managed to couple the logic all the way from the instrument and spacecraft workings all the way to demonstrate whether hypothesis 1 is true versus hypothesis 2 is true. It was quite impressive. It took hundreds and hundreds of hours to do that work. And that's before you even introduce that into the more common framework. So don't underestimate the complexity of these sorts of coupled science engineering problems. If there were a common framework, it would have simplified things in some ways. But at the same time, they would also then need to be trained to work in that common framework. So maybe a digital twin is the way to do it. And I want to thank James Keane for the original artwork and me destroying it by giving a fake twin bit of graphic here. Is this the right approach to such a complex and often unique problem of designing a mission? And thinking forward, this isn't just about the formulation process. And so first of all, digital twins are, at least to a large extent, not just simulations. I think we've already discussed that. They are, as much as anything, about the interactions of the physical world, which is changing goalposts, really. The world around you is not doing what you expect it to do. But really, that's the science community. Our models change, our ideas change. There are massive moving goalposts all over the place. And that happens at the cadence of formulation. New things are changing all the time. When you get into beyond the stage of formulation, and you go, having a coupled simulation could be useful for that, then you're also testing your hardware. You may be finding out that your MOSFETs aren't working as expected. And so if you had, within the common framework that you've been using all the way along in the mission, had a way of putting those surprises into a toolbox that would allow you to predict what the effects of that on the design were concerned, I see value further down the road. And again, that's a real-world iterative feedback there. And then, of course, once you've got your mission, you're also recalibrating. Your instrument calibrations are drifting over time. You can incorporate some of that. Maybe you've got some pixels dying in your sensors. And then when you collect data, well, guess what? Your science models perhaps aren't working as you expected. None of the working models really fit the observations. And so the ability to react to that also could be valuable. So we talked a bit about whether this is valuable in the formulation process. Yes, but perhaps as much of the value is by setting yourself up for success after pre-phase A and phase A activities, through phase C, through phase D, through phase E, maybe even phase F when you discover that your data have issues when you're archiving them. And so it's not just about formulation here, and there are ways of iterating with the real world, even in a data-poor planetary mission. I mentioned the DIKW framework. Apparently DIKW is something where it's contended as to where the concept came from, and some people blame T.S. Eliot, so I thought I'd quote the lines from choruses that this comes from. But in the end, I think we should always bear in mind that no matter how intricate our models are, it's all about generating scientific knowledge and ultimately wisdom. And so it is the science that this has to be anchored in. I think without the model of the universe, the bite-sized chunks of the universe that allow us to advance science, a digital twin concept is just an engineering simulation of something that we haven't got real-world feedback until way further into the mission. So I'm going to stop there. It's a little shorter than intended, but hopefully we can have a bit of a discussion about some of these elements. Thank you.